Our recording is rolling. So it's Wednesday, February 15th. I got this lab lined up for you guys today. You guys got this page in front of you. Okay, and there was a faculty meeting this morning. It sounds like you guys heard from your other classes too that they're gonna crack down on cell phones, especially starting about a week from now. So this is coming from the district. Yeah, so there you go. I know in this particular class, I have you guys use your cell phones for quite a few things, like stopwatch functions for labs or like Kahoots, but they want you guys to instead use your laptop, so they give you guys a few back for all that kind of stuff. So, that's what we're doing. Okay, so tomorrow, do different things for different classes, so get there when we get there. But let's focus on this lab. So you guys remember yesterday, I took you through a PowerPoint on different principles, properties of matter. And one of the things we looked at was Archimedes' principle. Do you remember that? And Archimedes' principle, what did that say? That said that the buoyant force is equal to the what? The weight of the displaced fluid. Right. So say if you have a boat and you have a boat sitting in the water, it's pushing some water out of the way. If you know how much water that is, if you were to weigh it, that's equal to the force upward, which should match the weight of the boat if it's floating there, right? And that's what we're that's gonna be a physics flyover to what we're going today. So I'm gonna walk you guys through this lab, like how to do it, how to set this up, and then I will give you guys a square of aluminum that is 12 centimeters by 12 centimeters, just like this picture, square of aluminum. And you guys can pull up the side to make a box boat. You guys see this box boat right here? So here, let me make one just to show you guys the mechanics of how to do this. Actually, I probably want to measure because they're giving me some measurements as well. Maybe I want to do 1 centimeter. Bam, that's 1 centimeter right there. Let's say I measure that, throw it on my ruler, make a nice crisp fold one that's 1 centimeter. Okay. And I'll do that all around the perimeter. So 1 centimeter on the other side. Make believe I measure that a little bit better. So let's call it 1 centimeter. Okay. Then 1 centimeter right here. Bam. And finally, 1 centimeter right here. Bam. Right, nice crisp fold. Okay. Now the corners are going to have to push over. Right. And box boat. Just like that. You guys see some tubs of water in front of you? Tubs of water. So after you build your box boat, you can toss this in the water. And then you can start adding lab weights to it. If they're little tiny lab weights, this one here is probably about as large as one you want today, right? So I put that in there, and maybe that floats, or maybe not. Maybe this box boat isn't good enough. Do you guys see it has some volume to it? Some volume. Do you think what if instead of folding 1 centimeter over, what if I went 2 centimeters? Do you think it would have a larger volume? Huh? What about 3 centimeters? Like if I keep folding and folding and folding, at some point the volume's going to stop increasing and actually start to decrease. And you know it's going to be okay. Here, guys, look up here. What if what's the maximum that I can fold an edge? Like here, I just showed you guys 1 centimeter, right? Remember, this whole thing's 12. So if I'm folding around the perimeter, what's the maximum that here? Say I call this X. What's the maximum that X could be? 6, right? Because once you go to 6, you've effectively just folded it in half, right? Okay. And in fact, if you do that and you go that around the perimeter, you're back to how much volume is that right there? You're back to 0 volume, right? As if you never folded it all. That's never going to float. You fill that bar just straight to the bottom. So I wonder what is the optimal design boat that I can make, you know, using this method. Like, what is the optimal X, like maximize the volume, therefore maximize the weight that it can carry, right? So that's where we're going with this. We're going to tie together math, Archimedes principle, physics. Okay, so goal: design a box boat with limited materials. In this case, your materials constraint is a 12 by 12 square, 12 centimeters by 12 centimeters, to maximize the weight that the boat can carry. So let's kick this off with some physics. Draw a free body diagram for the floating boat. Say we're looking at this boat right here. We're looking at it from the side. Wait, bring up the boat again. Right, box boat. Okay. And I'm looking at this boat from the side, right? So kind of from this perspective right here, right? Looking at it, okay? And I'm looking at this right here. Can you guys draw a free body diagram for that boat floating? So everybody's doing this now. Oh, so you guys wrote your name on your paper. Okay, you guys wrote your name. Okay. And now you guys drew that there's a weight down and a buoyant force holding it up. And those two would be balanced, right? Right. Not because of Newton's third law of motion, but because it's in equilibrium, right? Okay, guys. All right. So buoyant force, or so let's dig into these equations. Buoyant force equals. I told you guys Archimedes' principle yesterday. Buoyant force is the weight of the fluid displaced. In this case, the fluid is water because you guys have a tub of water for you. That's what it's putting in. Okay? And then we took that expression, we broke it down into three variables multiplied together. Who remembers what's the three variables multiplied together for buoyant force? It's like how about density of the fluid? In this case, water. Right, Greek letter rho, density, times the displaced volume. So maybe like V displaced. Okay. Now that right there, if you multiply those two together, you get the mass of water displaced, right? That's what density times volume is, it's the mass. Here's how do you go from mass to weight? Just multiply by, yeah, gravity field, G. Right? Just like that. Okay. Next line, what is weight equal to? What's it been all year? N times G, right? Now this would be the mass of the boat times the gravity field, right? And the mass can include, well, I guess the foil itself, which is a little bit, plus whatever you stack in it. Okay. Like this guy's 100 grams, right? It's 0.1 kilograms in base SI units, which is actually going to be kind of an issue today. Is be careful about like mixing matching units, right? Because at some point later on, and I'll help guide you guys through this too, you're going to have to calculate forces. And guys, what's force measured in? Newtons. And Newton breaks down into kilogram meter per second squared. Okay. Okay. But at your desk, what's probably more convenient to work with and think in terms of is not meters, but centimeters and not kilograms. Here's 1 kilogram, but maybe like grams, which is probably more feasible. Right. So here, what is the density of water? That's what this says, right? Rho water. What's the density of water? What's one value for density of water? Okay, yeah, 1 gram per cubic centimeter. So like if you draw 1 centimeter by 1 centimeter by 1 centimeter, you guys see this little box right here? That's 1 by 1 by 1 centimeter. So 1 cubic centimeter. If you fill it with water, that has a mass of 1 gram. Okay. What about this? What about cubic meter? You guys see the tiles on the floor? You guys see 3 tiles? 3 tiles is a little bit short of a meter, but it's pretty close. Okay. What if you go 1 meter by 1 meter by 1 meter? You guys see this big old box? Big old box? Okay. If it fills out with water, how many kilograms is that? 1,000. That's 1,000 of these guys right here. Okay. Okay. So, what number do you want to use in your math? Well, probably like contextually, it's easier to work with 1 gram per cubic centimeter. But remember, when you're calculating force, you got to switch over and think about like in terms of this, right? 1,000 kilogram per cubic meter. Okay. Next line. Gravity field. What's one value for gravity field? Could you do 9.8 meters per second squared? Or if you want to, you can call it 10 meters per second squared. It's so close. Okay. And there were at least a couple labs last semester we did where I remember Atwood we did like centimeters per second squared. Okay. So how many centimeters per second squared is that? How many centimeters in a meter? 100, right? Okay, just like 100 cents in the dollar. Would this be 980 centimeters per second squared? Okay. Okay. Again, maybe more intuitive for something like that. Okay. So just think about different values in different units. Okay, so hold on to those ideas. We're going to come back to this later. Okay. All right, so we're back to the box. So I'm going to give you a 12 centimeter by 12 centimeter square. Okay. You guys can fold it just like I showed you guys into this box. And now we've got some variables going on. So however much you fold it up, I was showing you guys 1 centimeter, for example, but let's in general call that x. That could be a variable. Okay. And the more you fold up x, isn't this y going to shrink? And this will have a base of y by y. You guys see that? Okay. So the volume of the box, wouldn't the volume of the box be, or actually, whoops, I'm getting a little ahead of myself. Okay. Oops. Let's go through these questions one by one. What is y in terms of x? Like here, for example, let's do some numerical examples. If x is equal to 1 centimeter, it's 1 here and 1 here. What is y equal to? How many centimeters? 10. Right, 10 centimeters. What if I make x 2 centimeters? What is y? 8. Right? In general, in terms of x, you're going to start with 12 centimeters. And you're going to subtract off what? Yeah, 2x. it's always going to be 12 minus 2x for this particular square of aluminum, right? This foil. Right? So here, if you plug a 1 here, 12 minus 2 by 1, oh, it's 10. If you plug in 2 for x, 12 minus 2 by 2, oh, that's 8. Just like you guys told me. Next line, what is an expression for the volume of the boat in terms of x and y? Oh, well, we got it right here. Oh, guys, what's the answer to that question? Yeah, y times x, right? Because length times width times height is not y times x. Hey, could I call that y squared times x? That's what that would be, right? Sure. But you know what? This x and this y are not independent of each other. That's what we said for the last question. Y is related to x. So could you substitute in for y, this expression right here? Okay. And that's the next question. Can you get the volume of the boat as a function only of however much you pull up the tide, which is what x is? Okay. So here's what I'm going to do a little bit of math up in the corner of the paper here. I'm going to go volume equals. Now it's y squared x, but instead of y, I'm going to put in this expression which represents y. 12 minus 2x. I'm going to drop the centimeter unit, just make it look cleaner, right? And that's all squared, because y squared, and then it's multiplied by x, right? Can that be true? Okay. You guys see the next step? FOIL, F-O-I-L. You guys remember FOIL, F-O-I-L? Algebra, device. So can I do F O I 24 is 48 x. See, negative and negative makes it positive. There's FOIL, right? And I still got this x on the outside. Sure? Ooh, can I distribute? Can I do that? Distribute, right? And that will give you the volume of the box as a function of x, which looks like this. Ooh, got like a cubic function. Interesting. Right. Everybody get so far? Now there's this italicized stuff. I'm going to come back to that. But let's look at this table. So table, you could plug in different values of x, and then everything else should follow from that. So let's go. You could not fold at all. You could fold 1 centimeter, 2 centimeters, 3 centimeters. You could even do non-integers, right? You could do like a 2.5 if you wanted to. Right, test that out. Okay. So try different things. Okay. What if you don't fold at all? What is y equal to? Yeah. So like all 12, right? Okay. And then here you can also play off this, right? 12 minus 0 is just 12. What would the volume of that boat be? Yeah, that would be 0 cubic centimeters, which you could play off either one of these. Okay. 0, 0, 0, 0. Okay, that's not very exciting. 1 centimeter. Ooh, guys, if x is 1 centimeter, what is y equal to? 10 centimeters. Or so you guys told me that a few minutes ago anyway. Okay. And if this is 10, and this is 10, and this is 1, those are all centimeters. What is the volume of that box in cubic centimeters? 100, right? 10 by 10 by 1. You guys get it? Okay. So shouldn't this be 100 cubic centimeters? Would that be the case? Okay. But you know what? We came up with a general expression for the volume just in terms of x. Hey, shouldn't that be consistent with this right here? Shouldn't we be able to plug this 1 centimeter into this and get it that way? Let's test out this expression and see if this really works. I'm going to plug in 1 centimeter everywhere I see the x. Okay. So 144 times 1 minus 48 times 1 squared plus 4 times 1 to the power of 3. And there's only one thing that can pop up on my calculator screen. What does the answer have to be? Has to be 100 cubic centimeters. Oh, it is. Okay, you guys get it? So that's math, right? So all the FOIL, all that, but the whole process worked, right? Okay. Do you guys think you could go through the rest of the table and figure out, and like make up your own x values and fill out the rest of the table? Could you guys do that? Okay. Except there's this last column that I haven't talked about. So let's do it. Says force buoyant maximum. So it's maximum buoyant force. Measured in newtons. Okay, now here's where I made that whole deal earlier about mixing, matching units. Like guys, if you're trying to solve for a force in newtons, do you want to work with grams and centimeters or kilograms and meters? You have to do kilograms and meters, right? Because that's what Newton breaks down in terms of 1 Newton is 1 kilogram meter per second squared. Okay, so let's do a little shortcut on this. The maximum buoyant force, okay, well, which would also represent the maximum weight that the boat could hold, right? Because this and that are just balancing each other out. Maybe the boat's sitting so low in the water, it's holding its max as much as it can. So here's the force, and I'm substituting in the values in terms of base SI units. So the density of water is 1,000 kilograms per cubic meter. Gravity field is 9.8 meters per second squared. Now the displaced volume. Now here's where you have to switch from cubic centimeters to cubic meters, because you guys know it's cubic centimeters, right? Like what is the volume of this box in cubic meters? Well, it's probably a tiny, tiny decimal of a cubic meter. 1 cubic meter is a huge box. This is a tiny fraction of that, right? So I gave you guys a hint how to do that. I printed it on the other side. If you guys flip over your paper real fast, you see it down the bottom? It tells, oh look, it's a dimensional analysis table. Hasn't dimensional analysis been really handy like throughout the entire year? Here's how you can convert from cubic centimeters to cubic meters. You just divide by 100 3 times. So divide by 100, divide by 100, divide by 100, and the units all work out like that. Right. So that's what I did right here. I took 100 cubic centimeters and divided by 100 3 times, that's the power of 3. And that represents the volume in cubic meters, which could be a tiny decimal. Anyway, you put that all together, and I'm getting 0.98 newtons. Now, it's specifically for a 100 cubic centimeter box. It can hold up to that much weight. At that much weight, this would be sitting so low in the water, it'd be going right up to the brim. Like if you like came up, if a piece of dust went like settled on here's that weight equivalent, 100 grams, that weight equivalent. So here comes a piece of dust, and then this whole thing sinks to the bottom. So this right here is 0.98 newtons. Okay. Okay. Now, for the rest of this table, I'm going to give you guys a shortcut. You guys, my shortcut? Okay. Do you guys think that the volume of the boat and the maximum buoyant force are going to scale up directly proportionally to each other? Like, for example, if you triple the volume of the boat, that would also triple the maximum buoyant force. Right? Triple the weight it could hold. Right. Maybe you can see that right here. Right. That would be true. This is a direct relationship, linear relationship. Okay. So what I'm trying to say is, guys, 0.98 newtons. Is that basically 1 newton? In fact, if you call that 1 newton, that'd be so close. I would take that. 1 newton. So if you know the volume in cubic centimeters, what do you divide by to get the last column? 100, right? You guys see that? So whatever crazy number this number is in this column, can you just divide by 100 and get the last column? Okay. Now that's a shortcut. This is the long way to do it. But okay. You guys get that? All right. All right. Now back to this bit that I skipped over, this italicized bit. It says calculus students use calculus to determine the optimal dimensions of the boat. Right. So show of hands. How many of you guys are taking calculus? Who's taking calculus here? Calculus. Wait. Let's see. A couple of guys were. No, maybe. Right. Okay. Well, let me tell you guys a little bit about calculus. Calculus is about instantaneous rates of change. It's come up a few times in this class. Like the instantaneous rate of change of displacement is velocity. Instantaneous rate of velocity is acceleration. So you guys have kind of seen this before. In this case, what are we talking about? Well, as you increase x, as you flow up these sides more and more, the volume changes. At first, the volume increases. So the rate change of volume would be positive with increasing x. But at some point, that's going to change. Because if you make x like 5 centimeters, here's 5 centimeters, 5 centimeters. Now I'm going to have a tall, skinny boat. If I do that to this side and this side too, and then make like a tall, skinny boat, which would have hardly any volume. So at some point, as you increase x, volume is going to turn around and start decreasing. So volume is going to increase, and then it's going to decrease. And what you can do with calculus is you can take, here's volume just in terms of x in general. You can take the rate change in this equation, set that to 0, and where it goes to 0, it would stop increasing and start decreasing. And you can solve for x, and that is the answer to this question of exactly how you should make the boat to optimize or to like maximize volume, right? So anytime you have an optimization question, you can solve it with calculus. But in this case, you don't have to. You can just guess and check, and like you don't have to take calculus to this lab. You just it's an easy way to get to the answer really fast. Okay? And so circle the row of the table that represents the optimal box boat. So whichever one can hold the most weight, or for that matter, which one has the greatest volume. These go hand in hand. Right, so circle the row that does that. I'll leave that to you guys. Okay. Test your boat empirically. Here's the science portion of this. So once you got your boat, you can start throwing these lab weights in it and see like how much weight can it hold. Okay. And then answer in newtons. And by the way, the flat column is also some number of newtons. So it looks like we're dealing with the order of magnitude pretty close to like a newton, right? Somewhere there, maybe over a newton, but pretty close to 1 newton of weight. This right here weighs 1 newton. It's 100 grams. Okay. Right. You guys good so far? Okay. All right. On the back, there's a couple of graphs. So I'll get you guys started on the graphs. One graph is what is y in terms of x. The other graph is what is the maximum buoyant force, like the maximum weight it could hold, effectively, as a function of x. So they both have the same horizontal axis. They're both like how much do you fold up the side. Okay. And we already have some of the points for the graph. So for example, if x is 0, does that mean you don't fold it at all? You're just back to the flat sheet if x is 0. What is y equal to? 12. It's a full 12 centimeters. This is 12 centimeters. That's that point right there. Right? Did I ask you, I forget, did I ask you guys what's the maximum you can make x? What's the maximum you can make x? Yeah, you can go up to 6 centimeters, right? Because 6 centimeters would be like folding this in half, right? Folding in half. In which case, what's the volume of this back to again? 0 volume. Oh, well, whoops. Sorry, I'm getting ahead of myself. I asked the wrong question. What would y be equal to? Like the height of this boat, if it's flat. That would also be 0, right? Right. So isn't it this point right here? If you just fold it in half and fold it in half, you get 0 height. Right. And wait, did we do one more? We did do one more. If x is equal to 1, isn't y equal to 10 centimeters? So we've got the point 1, 10. In fact, you know what else you guys got for this graph? You guys already wrote the equation of this graph. What is the equation of this graph that you guys already wrote? Yeah, there you go. 12 centimeters minus 2x, right? 12 minus 2x, right? Or if you like, you could say y equals negative 2x plus 12. If you want sort of y equals mx plus b. Ooh, y equals mx plus b. Is that going to be like a straight line? Ooh, right? And you could do more checks on that, a lot more points, but it does. Right? Now the other graph, maybe a bit more interesting, a bit trickier. The maximum buoyant force is a function of how much you fold at the side. But you already have some points on this one too, because again, if you don't fold it at all, you're back to a flat sheet. How much weight is that going to hold? Nothing. So that point right there exists, right? That point right there, 0, 0. Yeah. And there's another point that you have. If you fold x to 1 centimeter, so that was the example I was going with. So if you fold up 1 centimeter and you go around the perimeter and you do that 1 centimeter all the way around, you know it can hold basically this guy right here, or up to that. Again, if you like, you could round that to 1 Newton. So it's a little bit less than 1 Newton. So 1 centimeter corresponds to a shade under 1 Newton. That's that point right there. Is that? But what else I told you guys is that as you increase x, at some point it's going to start decreasing. So if x goes all the way to 6 centimeters, what's the volume again? Yeah, now you're back to 0 volume. There's 3 points on the graph. You guys see it's going to go up, it's going to come back down. And I wonder, where does it max out? Because at some point it's going to reach a maximum possible buoyant force. So what is the x value that would max out? And what is that maximum buoyant force? I'll tell you guys this too. Technically, it's not a parabola, although it does make some kind of upside down shape. Right? This is part of a cubic function. Actually, it's proportional to this right here. It's like x cubed, right? You guys think this is actually gonna go kind of like this, right? Sort of. All right, who's got any questions so far? Any question? Yeah. Oh, what, this right here? Okay. Buoyant force. So buoyant force comes from Archimedes' principle. That's from the PowerPoint yesterday. So density of the fluid times gravity field times, which is mass of water displaced, times, or sorry, I got to fix that. Rho GD. So rho times V is the mass, times G is the weight. So the weight of water displaced. So here's the density of water in base SI units. Here's the gravity field in base SI units. Now your volume you have to convert to cubic meters, and you do that by dividing by 100 to the power of 3. That converts from cubic centimeters to cubic meters. Okay? So you run the water, the numbers for the specific example I gave you guys, and you get 0.98 newtons. Right. Now, I also gave you guys a shortcut for this. I said, now that you have this, and you know there's a direct relationship between these two, whatever your third column is, you can basically divide by 100 and get your fourth column. That's kind of a shortcut. Okay? Guys get that? Okay. So for the rest of the class, I need to give you guys these squares. Right? So you guys got a solid 20 minutes. I'm going to give you guys these squares. You guys can fold your boats. You can go back and refold them. You can change the shape. You can test it in the tubs of water. I want you guys to find out what is the optimal boat shape. So how much should you fold up the side? Right, circle that row, whatever the answer is, and make the two graphs on the back. Right, oh, okay. So once you got the two graphs, you got the optimal shape, and you got the maximum weight empirically. Then turn that into the gray tray. So that's all we got. I'll walk around, help you guys out.